All right, so we're back. All right, keep working on chapter 16. Now we're going to talk about combining random variables with other random variables and with constants. So the question is, what do we do when we have more than one random variable? Well, we want to know the expected value of individual random variables. We want to be able to deal with multiple events. Okay, just a single random variable, that's good, but we want to be able to deal with multiple independent random events. Not going to worry about too many multiple events that are dependent. But for multiple independent events, these you should be able to deal with. These would be fair questions to ask about. So, rules for means. In order to go over these, you want to look at page 373 in our textbook. Okay, page 373 is going to go over a lot of our rules. Sorry for that. So you make sure you're going over these rules. Now, rule number 1, if x is a random variable and c is a fixed number or it's a constant, then the expected value of x plus that constant, that's just going to be equal to the expected value of x plus the constant. And if it was minus a constant, it would be minus the constant. This is our first rule. This is kind of nice. So let's just say I have a dice and I roll it. Every time I roll it, I'm going to subtract 1 from the findings. So I'm going to subtract a constant every time I roll the dice. Well, think about it. If the average dice roll comes out to be, say, 3, if I subtract 1, it would be really nice that the average would just be, well, 3 minus 1. And it turns out for that it works. So the expected value is just going to be the expected value plus or minus that same constant. Now for variances, the other way we can write this is the mu of x plus c is just equal to the mu of x plus or minus c, whatever we did to it. If we added 1, we're going to add 1. If we subtracted 1, we're going to subtract 1. If we had to subtract 10, we're going to subtract 10. Whatever I did, the expected value is just going to change by the same operation. Now we know from earlier chapters, if I add or subtract a constant from data, it moves the mean, but it doesn't change the variance or the standard deviation. This is the same concept. Expected value is a mean. It's a position. It's where should something be. If I add or subtract, it should move that. Okay. So let's try a simple set. It just has 1 and 3. If I take the average of that, well, the mean is 2. But let's just say I added 5 to every element. So this time, it's 5 plus x, it's 6 and 8. So if I look for the mean of s of 5 plus x, that's going to be the mean of 6 and 8. Well, that's 7. But that's the same as if I just added 5 to the previous mean. It worked out exactly like we thought. Okay? So in this case, what we're saying about the mean is the expected value of x plus 5, well, that was the expected value of x plus 5. So expected value works really nicely. It works the way we think it should work. It works the way we want it to work. So it works really well. If I just add to everything, then the mean, I'm just going to add to the previous mean. If I subtracted from everything, I'm just going to subtract from the expected value. Now, next we have, what if x is a random variable and a is a constant, but this I'm going to multiply it. So I'm going to multiply some constant times everything. Well, the rule says the expected value of a times x is equal to a times the expected value of x. Or I could call it mu of sub ax. Well, that's equal to a times mu of x. It's the same thing, just a different format of writing it. Now let's look at that group again. The mean of 1 and 3, turned out the mean was 2. In this case, let's multiply everything in the set times 5. So now we get 5 and 15. So if I take the mean of this, we get 10. But that was the same as me multiplying the previous mean just by 5. It worked out exactly like we wanted it to. So in this case, the expected value of 5 times x, well, that was just equal to 5 times the expected value of x. It works out the way we'd like it to work. It's nice and neat and simple, and the expected value just works well. If I have to add, I'm going to add to it. If I have to subtract, I'm going to subtract from it. If I multiply, I'm just going to multiply. It works really well with us. So what if I have 2 random variables? Well, the expected value of x plus or minus y, well, that's equal to the expected value of x plus or minus the expected value of y. So if I was adding them together, I'm going to add their means. If I was subtracting them, I'm going to subtract them. It just works really well for us. I could also write it as mu of x plus or minus y. Well, that's equal to mu of x plus or minus the mu of y. There's just another way of writing it. You have to be able to see it both ways. So let's try it. Let's have s of y. S of y could be 5, 9, or 22. Those are 3 values for y it can take on. So the mean of this, well, that's 12. Now I'm going to make the set of x plus y. And it's a little tricky. Remember, x had the values 1 and 3. So in my new case, all the possibilities. Well, 1 could be added to 5, or it could be added to 9, or it could be added to 22. 3, the same thing could happen. It could be getting added to 5, or to 9, or 22. These are random variables, saying the different values. So because I'm combining them, I had 2 things in my first set, 3 things in my second set. That's 2 times 3. I should have 6 things in my combining set, and I do. So it works out. These are the different values I could take on in my new set. If I take the mean of all these, the mean is 14. That's the same as finding the 2 means added together. The mean of x was 2. The mean of y was 12. 2 plus 12 is 14. Turns out it's the same. Or in this case, the expected value of s plus y, well, that's equal to the expected value of s plus the expected value of y. So it works out really well for us. Expected values work really well. They're just going to add, subtract, multiply very well together. Now variance. Variance is a little different. You want to go page 373. Let's go over these rules. Rule number 1, if x is a random variable and c is a constant, then if the variance of x plus or minus c, that's just going to be the variance of x. Remember, variance is telling about spread. It's talking about how things are spread out. By the way, we could also rewrite this another way. Sigma squared of x plus c, that's just sigma squared of x, or standard deviation squared. Variance is the standard deviation squared. Now, adding a constant will change the mean, but it doesn't change the variance. So the variance of x, that's the same as the variance of x minus 1. Now if we think back, this is like how we had to do a standard deviation. If you added or subtracted, standard deviation didn't care if you added or subtracted a constant. If you subtracted 10 from everything, well, your range was still the same range. You subtracted 10 from the minimum and the maximum. Your standard deviation didn't change if you added or subtracted to everything. That's what we're saying here. If you have a variance of a random variable plus or minus a constant, that's still just going to be your variance. Hasn't changed. So let's try it. Let's say I've got my new set, t. And in t, we have 10 or 14. Now if I put these in the calculator, let's pull that calculator up. All right. We go over here to edit. I've already got 10 and 14 loaded inside of L3. Let's find out, what is our standard deviation? So one variable, stats, and we want for L3. I don't need a frequency list because I don't have frequency. My standard deviation is 2, so my variance is 4. And that's what we found. Standard deviation is 2, variance is 4. Now let's add 5 to everything. I'll bring a calculator back over. I'm going to edit. And if we look inside of L4, we've got that. I've added 5 to each value, so it's now 15 and 19. Let's look up our standard deviation now. 15 and 19, this is in L4. So you tell it L4. And again, our standard deviation is still 2. And it's still 4. Because we didn't change how far apart anything was. Everything was moved by the same amount in the same direction. Everything's still the same distance apart. Variance didn't change. So now I come to rule 2. And remember, this was just like data shifting. If you added or subtracted to everything, the standard deviation, the range, the IQR, they didn't move anywhere. Let's go ahead and try our next one. Rule 2. X is a random variable, A is a constant. Well, this rule says the variance of A times X, that's actually equal to A squared times the variance of X. Or sigma squared of AX is equal to A squared times sigma squared of X. So let's take another look. We've got our group 10 and 14. Standard deviation of 2 and 14. If I multiply everything in that set by 5, we get this new set, 50 and 70. Let's try this inside our calculator, see what we get. So I go up here to stat. Let me see, get my mouse. Stat, edit. We have 50 and 70. Let's see, can I get that over there? Oh, I already have them typed in. Now let's find our standard deviation. This is stat, calc, one variable stat. We said this is now an L5. And my new standard deviation is 10. Oh. Let me make sure of this. Wait a moment. Hang on. Did I do this right? Let's look. Okay, yeah, our standard deviation. Okay, I did. I got nervous for a second there. My standard deviation is 10. But variance, I need to do 5 squared times that. I'd have to square this. I square 10, I get 100. Well, to get variance. My standard deviation is 10. That means my variance is 100. That is the same as 5 squared times the previous variance. The previous variance. The original variance was 4. 5 squared is 25. We do get 100. So it does work. Sorry. You see a standard deviation, you got to remember to square it to see that variance. So it's like, wait, did I do it right? No, we had it right. Should have trusted my calculator. I knew the rule worked. Should have trusted it. Now, rule 3. If x and y are random independent variables, or independent random variables, well, then the variance of x plus or minus y, well, that's going to be equal to the variance of x plus the variance of y. Notice this little bit of a difference now. Variance of x plus or minus y is always adding the variances. They never subtract. Variation will not decrease because you're now subtracting variables. Okay? If you subtract them, it's still going to increase the overall variability. Or we describe it this way. It means the same thing. So let's talk about this set. Now we have 6, 9, and 12. Oh, let's pull up our set here. 6, 9, and 12. Let's put that in here. Our calculator back. So our first one, x. Our very first time we had x, it was 10 and 14. But let's think about that. Well, I could have 10 plus 6. That'd be 16. I could have 10 plus 9. That's 19. I could have 10 plus 12. That's 22. Or I could have 14. 14 plus 6 is 20. 14 plus 9, that's 23. 14 plus 12, that's going to give me 26. Now let's try if we subtract them. We go over here to L2. We'll put those in here. 10 minus 6, that's 4. 10 minus 9, that's 1. 10 minus 12, that's negative 2. Then we had 14 minus 6, that gives us 8. 14 minus 9, that gives us 5. 14 minus 12, that gives us 2. Now we're saying that standard deviation, and let's say our standard deviation of, let's get those in there, 6, 9, and 12. 6, 9, 12. So let's get this standard deviation first. Stat, calc, and this time L3. So our new standard deviation is 2.449, and we got a bunch of other numbers on there. And if I square that, I'm going to get 6, actually. So my standard deviation and variance are 2.4494897, and they're 6. So if they're independent, and I subtract them, in this case, I did 10 minus 6, what we have here, that's going to turn into negative 2, 1, 2, 4, 5, 8, and we did that. Remember, that's what we had here. Go back into it. We subtract them. That's our L2. Negative 2, 1, 4, 5, 8, and there's our 2. So let's find that standard deviation. So that's going to be L2. Stat, calc, 1 of L2. This we find. 3.162277. That's what we find. Now remember though, if we look at this, Our variance is that squared. In this case, it's 10. Well, our variance of t was 4, and our other one was 6. It still turned into adding them up to get the new variance. You should have had those jotted down. A little tough there. Let's go back again. Our original variance for t of x was 4. That's our value right over here. It was 4. 25 times 4, that was our variance. We combined them, even though we subtracted with these values, it still turned into the variance of them combined being 10. And we can even verify that. We ran in the calculator, 3.16227, so 3.16227. We'll square it, see if we get almost 10. 9.995, because I didn't quite put all the decimals that I have to. I'd have put 2 more 6s on there. And we had gotten 10. This was equal to the sum of the variances. So the variance of the sum or difference is equal to the sum of the variances. And if you go ahead and construct it as x plus y, you'll find the exact same variance occurs. You're still going to add them to get it. In fact, we built it. So let's go ahead and actually look at that. We built that set. If we look, where our mouse go? We have that set where we added them right here in L1. So to stat, calc, let's run on L1. If we look, 3.1627766, if I square my standard deviation, I'm going to get that variance of 10. Adding or subtracting, we end up the same way. So adding or subtracting variables, you are still going to add or subtract the variances. Now, in a nutshell then, the mean of the sum of 2 variables, well, that's the sum of the means. The mean of the difference of 2 variables, well, that's going to be the difference of the 2 means. And if the random variables are independent, the variance, sum or difference, is always the sum of the variances. So I have random variable x, random variable y. I don't care if I add or subtract them. The variance of those being added or subtracted will be the sum of the variances. I will always sum variances. Variability increases. It doesn't decrease. So let's say you play a 3-digit lotto, pays $500 if you win. How many 3-digit numbers are there? Well, 10 times 10 times 10, we get 1,000 3-digit numbers. Your chances of winning then are 1 in 1,000. So let's have x is a random variable. That's the amount you win when you play this game. So take a moment. I want you to think about this one and start thinking about what might this look like if you're to play this game. What are we going to run into? What are we going to look like? If winning, you win $500. So think about what it looks like if you get winnings. Take a moment, jot down what you might get. What's our x? X is our random variable, represents the amount you win. Well, in this case, it might look like this. X is the amount you're going to win. So what you win, well, and then P of x, probably you win that amount. First time, you might win nothing. You don't win the game. So what's the chance that happens? Oh, or you could win $500. So let's think about that. Chance you don't win anything, well, there's only one way to win. So the chance you don't win, 999 out of 1,000. Chance you do, it's 1 ticket, 1 out of 1,000. Well, if I took the average of 0 and 500, I get 250. But does that make sense in this situation? The answer is no, because you're not going to win 500 just as many times as you win 0. You're much more likely to win nothing than you are to win 500, so I can't just take the regular mean. Instead, I have to find the expected value. If I do that, well, 500 times 1 out of 1,000 plus 0 times 999 times out of 1,000, you win 50 cents. So take me out of a candy shop, buy me some bubble gum. Our variation, though, our sigma squared, 500 minus that 50 cent squared times the 0.001 plus 0 minus that 50 cents squared times 0.999. We get a total variance of $249. Our standard deviation is $15.80. This is why people get into gambling. They only pay $1 to play. But that variability, that's a big variability. That's why gambling can be exciting. You only pay $1, but you could win 500. There's a lot of variation between winning and losing. Huge difference there. Okay, that's why people get into gambling. But you buy a $1 ticket. In this case, your winnings will now be what you win minus the dollar you spent on the ticket. And this is a part a lot of people forget to do. They forget to account for, you got to buy that ticket. You got to pay for that insurance policy. It's not free. If you don't account for this, your expected value is going to be off. Well, our rule says the expected value of X minus a constant, well, that's equal to the expected value minus a constant. In this case, your expected value was 50 cents. Now you got to subtract your $1 to play. Now your expected value is negative 50 cents. Every time you're going to lose an average of 50 cents when you play this game. You might not lose 50 cents every single time you play, but on average, in the long run, overall, you're going to lose 50 cents. Now, the rule says variance stays the same. You add or subtract a constant, variance doesn't change. So your variance is still 249. Standard deviation is still 13.8. Whether you pay $1 to pay, if you pay $5 to pay, doesn't matter, stays the same. So, imagine if the payout was doubled though. Okay. Oh wait, so don't play. But let's say payout gets doubled. What's your mean and standard deviation now? So our expected value of doubling it, that's E times 2x. That's 2 times the expected value. Okay, we've doubled the payout, so our expected value is now $1. So if I have to pay $1, I subtract, I break even. My expected payout's breaking even. Let's talk about variation though. That 2 doesn't become a 2, it comes out and gets squared. So our variation is now 4 times 249. Our variation now is even bigger. Prizes have doubled, but you still only pay $1 to play, hopefully. And our standard deviation, well, again, we take the square root of that whole thing, and we'll get our standard deviation is now $13.61. So our standard deviation increased also by doubling prizes. Now, thing to remember here, let's compare that. What if you played the game 2 different days? Are those independent events? Yeah, playing one day shouldn't affect the odds a second. So expected value of playing on 2 days, that is not E of 2x, that's E of x plus E of y. You're not doubling it, you're playing it twice as many, you're playing it twice. You didn't double it, you played it twice. So now it's 2 random variables being added together. So it's expected value plus expected value. Still turns out it's the same, 50 cents plus 50 cents $1. But the variance, what's our rule for that? Oh, variance of x plus y. That equals the variance of x plus the variance of y according to our rule. So it's 249 plus 249. We have 499. This is smaller than when we doubled it. When we doubled it, it was 999. Variance of playing twice is not the same as doubling the variance. So playing the game twice is not the same as doubling the payouts from the game. So make sure you keep these ideas separate. If I give you a problem that I say something was done twice, you can't just do 2 times. It won't work, especially not for variance. Standard deviation, again, standard deviation of x plus y, you take the standard deviation of that sum, $22.35. That's different. You can't just add them together. See, you add them together, you get $31.60. That ain't $31.60. You cannot add the standard deviations. You can add variance, you cannot add standard deviations. Remember, variance of independent random variables, they add. The standard deviations do not add. Do not add standard deviations. And that's it. So at this point, everything you need in order to do these questions out of Chapter 16 has been covered. Chapter 16, we did questions 9 through 16 and a couple we're going to do inside of class. Look forward to seeing you soon.